Welcome to another edition of Math for Nerds. In this edition, we are going to prove this result, which says that every sequence of real numbers has a monotone subsequence. A sequence is said to be monotone if it is either non-decreasing or it is non-increasing. So, monotone non-decreasing means that the sequence an satisfies that an is less than equal to an plus 1 for all n greater than or equal to 1. Whereas monotone non-increasing means that an is greater than equal to an plus 1 for all n greater than equal to 1. Given any sequence an, we will be able to find a subsequence which is either monotone non-decreasing or monotone non-increasing. So let's see how we proceed. Let S be the set defined as follows. It consists of all natural numbers A such that ak is less than equal to am for all m greater than equal to k. So if you start at ak and look at the sequence starting from there, you will find that ak is the smallest term. It might happen that S is infinite. So if S is infinite, we can write S by using the well ordering principle that it is like K1, K2, K3, etc., where K1 is less than equal to K2, less than equal to K3, and so on. Now, note that AK1 is less than equal to AM for all m greater than equal to K1. So, since K2 is larger than K1, so we will get AK1 is less than equal to A. Now, AK2 is less than equal to AM for all m greater than equal to K2. Again, K3 is larger than K2, so from here we can conclude that AK2 is less than equal to AK. Similarly, by induction, we will be able to show that AKN is less than equal to AKN plus 1 for all n greater than equal to 1. And thus, AKN is a subsequence which is monotone non-decreasing. Now, let's look at the second case where S is finite or even empty. When will this be empty? So, note that if you have this sequence minus 1, minus 2, minus 3, minus 4, etc., there is no such case as that AK is less than equal to AM for all m greater than equal to. And this would be the case with any strictly decreasing sequence. So, it can very much happen that S is empty. So, let K1 be equal to 1 plus the maximum of S. So, since S is finite, there will be a maximum value, and if S is empty, then we say that max of S is. So, we have this K1. Now, since K1 is larger than max of S, K1 does not belong to S. This is an important observation that since K1 is larger than the maximum value included in S, so K1 does not belong to S. Now, what does that mean by saying that K1 does not belong to S? Since K1 does not belong to S, we can conclude that it is not true that AK1 is less than equal to AM for all m greater than equal to K. That means that there exists a K2 which is greater than K1 such that AK2 is less than AK1. This is an important point to note that since K1 does not belong to S, there would exist a K2 which is greater than K1 such that AK2 is less than AK1. Now, K2 being larger than K1 also does not belong to S, and therefore there would exist a K3 which is greater than K2 such that AK3 is less than AK2. And in this process, we would be able to generate a sequence K1, K2, Kn, etc. of natural numbers which has this property that there would exist a higher natural number, here we call it Kn plus 1, such that Akn plus 1 is less than Akn. So, what we have done? If you see this step, what we have done is that we have created a subsequence whose highest term is AK1 then AK2, then AK3. So we have been able to get a decreasing subsequence of A. Thus, we have shown that when S is finite or empty, we will be able to produce a decreasing subsequence of A. Whereas when S was infinite, we could produce a non-decreasing sequence of A. So in both cases, we have been able to show that there is a monotone subsequence of the real number sequence A. This proves our claim.